right, let's go ahead and get started. This is chapter 19. It's our real introduction to carbonyl chemistry. Carbonyl chemistry is not going to be entirely trivial. There are going to be a lot of reactions that we do today. There are going to be a bunch of synthetic methods we talk about. But it'll be great fun. Trust me. When we speak of aldehydes and ketones and carbonyl sort of stuff, we're talking, of course, about the carbon-oxygen double bond. The groups that we'll be covering in the next few chapters. Aldehydes, we have a carbonyl with a group of some sort on one side and a hydrogen. Ketone has two carbon groups on one on either side. Carboxylic acid will have an OH. Here, an ester will be an OR. Stick a halide on. This is an acid anhydride, so we have another acid group. If we had water, we would have two acids, and of course, this is an amide. We're going to focus today on aldehydes and ketones. Now, when you talk about aldehydes and ketones, nomenclature is actually fairly simple, fairly straightforward. Here we have a two-carbon aldehyde. Hydrogen on one side, carbon on the other. The rule says that the parent chain must contain the carbonyl. So obviously, here we have no choice. This is our parent chain. It's a two-carbon chain, so it's an F. It is fully saturated, so it's an F-an, as in alkane. And it's an aldehyde, so we stick on Al at the end. This again, our parent chain is going to be 3 carbons, so it's a prop. We have a methyl group in carbon 2, so it's a 2-methyl prop. Fully saturated, so it's an an. And again, it's an aldehyde, so it's an al. Note that when you have an aldehyde, you don't have to put a number because, quite obviously, it must come at the end of the chain, right? Has to. This is acetone, our organic chemist's greatest friend. This is also called 2-propanone. Again, 3-carbon chain is prop. Fully saturated, and it's a ketone, so it's an one, not an al. 3-carbon chain, so it's a 1, 2, 3, 4-carbon chain, so it's a bute. It's a butane. It's a butanone with a methyl group in carbon 3. So the same basic rules for nomenclature that we've used before. You can make it a little more complicated. If you have a multifunctional compound, or the carbonyl is on somebody else's chain, we're going to refer to a ketone as an oxo group and an aldehyde as a carbaldehyde. So with this thing, we have 1, 2, 3, 4, 5, 6, so it's a 6-carbon unit. We're going to let the aldehyde be carbon 1 because that's the lowest number. So it's a hexanal, except out here in carbon 5, we have a ketone. That's going to go in as an oxo group. So hexanal for this thing, and this goes in simply as 5-oxo. Here we have a cyclohexane, and we have an aldehyde stuck to it. Lots of carbons in the cyclohexane, so we're going to let that be our parent. And we're simply going to say that we have attached to our cyclohexane a carbaldehyde group. Cyclohexane, carbaldehyde. 2 words. This is our friend benzaldehyde. We've used it several times. Benzaldehyde, again, this is a carbaldehyde derivative of benzene. So we start off with benzene as our parent. We're simply going to put carbaldehyde on as our substituent. And again, this is benzaldehyde. Now, by the time we get to this point in the course, nomenclature is not really important on exams. Those are the easy questions, right? So let's look at some. Here we have a variety of compounds. As we look at these, our first one here, we have a cyclohexene. And we have a ketone up here. We're going to let carbon 1 be our ketone because it is a higher priority substituent. That means that our double bond here is going to be 3, 4. So carbon 3, we have a double bond. We would call this cyclohexene -one. And we have to put the 3 in to indicate where the double bond is. Cyclohexene -one. And again, number 3. We could call this a cyclohexene, an oxocyclohexene. That would be an alternate way to name it, but this is fine. This is simple. This is obviously going to be a derivative of benzaldehyde. We have a nitro group down here in carbon 3. We could just call this 3-nitrobenzaldehyde. Benzaldehyde is an acceptable IUPAC name. 1, 2, 3, 4, 5, 6 carbons. So this is a hex. It's a hexane, because there are no double bonds. And it's a hexane-one. But we have to say where in the world this carbonyl is, and that's going to be in carbon 2. 2 hexane-one. Once again, 1, 2, 3, 4, 5, 6 carbons. So this is the hexene. It's a hexene with our double bond in carbon 1, 2, 3, 4. So this is carbon 4. So it's a 4-hexene, 2-one. Any questions?
That 3-nitrobenzaldehyde, could you call that 3-nitrobenzene-carbaldehyde also?
Yeah, you could, sure. Could be a nitrobenzene carbaldehyde. Once again, on the exam, we're not going to do a whole lot of nomenclature. When we have a carbonyl substituent on somewhere, on somebody else's chain or somebody else's molecule, we will call this an acyl group. This is acetyl, so it's a carbonyl with a methyl. With a hydrogen, we would call this a formyl. And with a benzene ring, it would be benzoyl. Now, obviously, you can have other things, 2 or 3 carbons, but the thing is that you would drop the name and just add YL as a suffix. Let's look at some simple examples. Go ahead and jot down some names for these guys. Remember, we want the parent chain to contain the carbonyl. So for our first compound here, our parent chain is going to be the little 3-carbon loop here. We want to do the lowest number that we can. And so we're going to let this be carbon number 1. So we have the phenyl group as a substituent. Now the 3-carbon thing is going to be a prop and -one, basically acetone. Except in carbon number 1, we have a phenyl group. So we could call this 1-phenyl 2-propanone. Once again, the parent chain should contain the carbonyl. We do this carbon 1 to get our lowest number. Phenyl group is a substituent, so it's a 1-phenyl, and again it's a 2-propanone. Over here we have a 6-membered ring, so this is a cyclohexane. It's a cyclohexane with a carbaldehyde group and a methyl. We're going to let this be carbon 1. Carbaldehyde comes first in the alphabet, which makes this a 3-methyl. We could name this then 3-methyl cyclohexane 1-carbaldehyde. Now this is the official name. Frankly, I don't think you need the 1. But this is the legal name. I think that quite obviously carbaldehyde is going to be carbon 1, so you could leave it out. But again, it doesn't really matter. One, 2, 3, 4, 5 carbons. So it's a pentane derivative, right? And it's an aldehyde twice over. Because it's an aldehyde, we don't have to worry about numbers. Aldehydes have to be at the end. So we can simply say this is a pentane and it's a dialdehyde. We could do that with pentane dial. Our next one here, we're going to let the carbonyl be part of our main chain. So the aldehyde is going to be carbon 1. We have a double bond here in carbon 2, 3, 4. So it's a 4, 1, 2, 3, 4, 5, pentene. And we just happen to have an ethyl stuck here in carbon number 3. This is 4 pent for our 5 carbons, En for our double bond, 4N, and it's an aldehyde in carbon 1. We also have the ethyl group here in carbon 3. 3 ethyl, 4 pentene, al. The one thing that I left out of the name up here for the cyclohexane derivative was the stereochemistry. These are both equatorial, aren't they? That means that they are cis. They're 1,3 diequatorial, so they're cis. Legally, at this point in your career in organic chemistry, you can look at each of these and assign RS to them. That would be a little bit more rigorous, and I don't know what that would be. But it would be a better name, probably. Cis would work, though. Cis is certainly fine. Any questions? All right, what about ketones and aldehydes? We have an sp squared carbon, a carbon-oxygen double bond, and our bond angle is 120. We have a pi system sticking out here, orthogonal to the board. We'll see that the lone pairs here are sticking out in this plane, pi system coming out. A lot of the chemistry of carbonyl compounds is going to involve the lone pairs of electrons that are sticking out here. We're going to protonate them, we're going to do things to them, and that's going to make the carbonyl carbon even more electrophilic. Now it's time to go back and review the good old days of 234. How do we make aldehydes and ketones? One of the earliest things that we learned in 234 was that you could take an alkene and you could ozonize it. When you react an alkene with ozone, you form an intermediate ozonide. 3 oxygens basically just come and sit down on the pi system. What's going to happen, however, is that this ozonide is unstable when you work it up with zinc and acid. So this is a dissolving metal reduction. You effectively split the carbon-carbon double bond. We split it right here, and both sp squared carbons wind up as carbonyls. Very nice, very clean reaction. Again, ozonolysis of an alkene. Straight 234. Any questions? If we want to split a substituted alkene, we can do this with ozone, again with zinc dissolving metal reduction, and we wind up with 2 ketones. We could also do this using potassium permanganate. Now remember, potassium permanganate is a powerful oxidant, so we can't use it to make aldehydes. Aldehydes would be immediately oxidized to the carboxylic acid. However, if we have a tetrasubstituted alkene, we can split this very nicely and again make 2 ketones. Any questions? Remember, we could take an alkyne and we could hydrate the alkyne. This is kind of a neat reaction. And it's an introduction to things that we're going to do in chapters 20 and 21. Because when we hydrate this alkyne, the mercury acts as a catalyst by chelating the triple bond, allowing water to add in a Markovnikov fashion, and we wind up with an enol. Now an enol is a really neat molecule, an OH and a double bond, but enols exist in equilibrium with ketones. It's in equilibrium with a ketone. What happens is we will lose the hydrogen here, the electrons will flow back, this will make a carbanion at this point, which picks up a proton, something like this, and we convert this into the ketone. In chapters 20, 21, whatever, we're going to deal with enols like this, except instead of adding it to a proton, we're going to take this incipient carbanion and use it as a nucleophile and do condensation reactions. It's actually a very neat sort of synthesis. But this is a very nice introduction to that. Enol in equilibrium with a ketone at equilibrium is 99.999% ketone, but there's always a tiny bit of enol in the mixture. We also know that if we don't want Markovnikov regiochemistry, we can cheat and we can do borohydride, or I'm sorry, BH3. BH3 and THF followed by oxidative workup will give us an alcohol on the anti-Markovnikov carbon. In this case, it would be this guy on the terminal. And just like before, this enol is going to rearrange spontaneously into the corresponding carbonyl. Electrons flow in, pick up a proton here, and we make, in this case, the aldehyde. Any questions on all of 234? Yeah.
Just a question on this one. The mechanism to break that triple bond to get to that. Could you
Well,
show it?
Could I show it? Actually, I can't, but you should have taken 234 with me. But what's going to happen is we're going to add the boron to the terminal carbon here. We add it to the anti-Markovnikov carbon, and what we do, we're going to transfer the hydride to this carbon. In the oxidative workup step, we dump the boron and replace it with the OH. All right, now we're back in 235. We also know that we can make ketones using a Friedel-Crafts acylation. If we take an acid halide of some sort and a good Lewis acid, we can produce the acylium ion. Very, very good electrophile. If we take this electrophilic center in the presence of a benzene ring, an aromatic ring, we can do a simple addition to form our sigma intermediate, lose our proton, regain aromaticity, and we make a ketone. Friedel-Crafts acylation. We just did chapter 17. In chapter 17, we talked about oxidizing alcohols to ketones and aldehydes. Once again, aldehydes are very, very sensitive to oxidation. So you have to be very, very careful. The one reagent that works very nicely is called pyridinium chlorochromate, PCC for short. Typically do it in dichloromethane. It will oxidize a primary alcohol to an aldehyde without going to the carboxylic acid. If we want to be a little bit firmer about it all, we could take a secondary alcohol and Jones reagent, which is basically just chromic acid, CrO3 sulfuric acid, dichromate, once again, this is typically an acetic acid. This will oxidize this nicely to the ketone. If, however, you tried this with a primary alcohol You do not get the aldehyde. Again, it over-oxidizes all the way to the carboxylic acid. So you want to stop at the aldehyde stage. You want to use PCC. There's one real exception, kind of a bizarre reaction, and that is if you happen to have an allylic alcohol. Now remember we said allylic was the carbon adjacent to a double bond. This is actually very reactive. If you remember this from SN2 reactions back in 234, the allylic carbon, as you do an SN2 on this carbon here, you get participation by the pi system. So that makes it very susceptible to lots of nice reactivity. This is a free radical reaction. MnO2 is an ugly sort of substance to use. In pentane, it's even worse. It doesn't dissolve. It's just this black mess. But it does oxidize it very smoothly. Allylic alcohol to an aldehyde, and it stops. You can do this with an allylic like this. If this was benzyl alcohol, it would also work nicely to make benzaldehyde. Kind of a special sort of reaction. Let's look at some. Go ahead and quickly jot down products from these guys. Our first one here, we have a benzoic alcohol, benzyl alcohol, and we're simply doing PCC oxidation. Remember, PCC is nice because it will not over-oxidize. It will stop it at the aldehyde stage, so we convert the alcohol to the carbonyl and simply make benzaldehyde. Our next one here is a little more aggressive. We're using Jones reagents, CrO3 and sulfuric acid. This is also called cleaning solution. You know when you work in lab and you wind up with a flask that's got this gunk in the bottom you can't get out? What you do is you put in chromic acid, sulfuric acid mixture. Let it sit for a little bit. It'll just eat out anything. It's amazing. Cleaning solution it's called. But it's a very good oxidant. It's going to simply oxidize the OH group here into a carbonyl. As long as you don't let it sit too long, it'll stop right here, and we'll just make the alpha-beta unsaturated ketone. This is a terminology we're going to use a little bit later, so let's just say it now. The carbon adjacent to a carbonyl is referred to as the alpha carbon, and the one next to it is beta. So this is called alpha-beta unsaturated ketone. We'll do this later. Again, we're using Jones reagent. We have a secondary alcohol. We're just going to oxidize this smoothly to the corresponding ketone. Any questions? All right, let's talk about carbonyl compounds and why we care about them. We've looked at the electrostatic potential maps of carbonyls, and basically they show a big positive end down here and a negative end by the oxygen. Quite simply, that's due to the fact that we have this resonance form where we can put a full positive charge on this carbon, a full negative on the adjacent oxygen. Now remember, resonance forms are neither here nor there. These are limits. And the real structure of a carbonyl is somewhere in between. But the bottom line here is that the carbonyl carbon will always carry at least a partial positive charge. So that means that anything with electrons is going to be attracted to this center. So let's look at some examples here. Here we have a simple carbonyl. I have two types of nucleophiles I'm going to react. One is a standard anionic, and this is, I did NuH2. Imagine the U wasn't there. This is an amine of some sort. So this is an amino compound reacting with it. That's the most common. If the nucleophile sees this carbonyl carbon, it's going to simply attack. When it does, it will form an addition intermediate that looks like this. Now it's important to know that this is an equilibrium. And sometimes this equilibrium is very, very unfavorable. Sometimes you make this and it immediately decomposes back to this. Electron move in, nucleophile moves out, and we're back where we started. This intermediate can sometimes have a lifetime of like 10 to the minus 8 seconds. So very, very short-lived intermediate. In order to move on to products, it's necessary to cap this, to trap the oxyanion, usually with a proton from the system, to make this guy. Moving from here back is much, much slower than this initial pre-equilibrium. If we happen to have hydrogens, our addition is going to be basically the same. We're going to add, we're going to form this intermediate, except now this is even less stable. This is a Zwitter ion. Zwitter ion is two charges in the same molecule. So this is a plus minus, and this has a huge tendency to go backward. In order for this to go on to products, we have to trap this by either pulling off this hydrogen or putting hydrogen here. When we do that, we can lose the elements of water, H2O, and form what we'll call an imine later on. Imine is a carbon nucleophile double bond, specifically with a nitrogen. We'll see lots of examples of that. Very important reaction in chemistry and biochemistry. Speaking of biochemistry, the carbonyl carbon is nicely electrophilic. Cyanide anion is a very good nucleophile. If we put a carbonyl carbon and cyanide together, they can react, and they form what's called a cyanhydrin. We pick up a proton, we have an OH and a nitrile group. Now once again, this is an equilibrium, but this is a good nucleophile, so these have a very reasonable lifetime. Probably the most infamous cyanhydrin is this guy, derived from our friend benzaldehyde. Benzaldehyde reacts with cyanide to give the cyanhydrin that has the name mandolonitrile. This is the oil of bitter almonds. If you go to the store and you buy a little vial of oil of bitter almonds and sniff it, by George, it smells like benzaldehyde. That's because it's really in equilibrium. But remember, as you're sniffing it, you're also sniffing one equivalent of cyanide. So don't do that a lot. Okay? Now, this has a real history to it. Mandolonitrile. The history starts with the actual compound that's isolated from peach pits, from almonds, whatever. Let's see, almond, whatever it's called. This stuff. This stuff became famous because it was supposedly a cancer cure. Now, the compound that was actually used to cure cancer wasn't quite this. Peach pits were much too difficult to come by. Instead, it was simply the halohydrin derived from glucose and benzaldehyde and cyanide. It looked something like this, and this was called Laetrile. Now, the sad thing is that this entire hoax was propagated by one of the great chemists, biochemists of all times, Krebs, but it certainly was a bit of a hoax nonetheless, and it still exists today. The logic that Krebs suggested was that Laetrile, if it was taken up by a cell, a tumor cell, could be cleaved. We're going to cleave the glycosidic bond, and when we do that, we would release cyanide, and the cell would die. So let's go back to peach pits. The enzyme that we would use here is beta-galactosidase. This is a beta linkage on the glucose ring. Beta-glucosidase will cleave this, and it will form this chunk and benzaldehyde cyanhydrin. Now, benzaldehyde cyanhydrin, we all know, is in equilibrium with benzaldehyde and HCN. Anybody ever encountered a stink bug? Stink bugs are kind of neat. They have this little pouch that they store benzaldehyde cyanhydrin. And they have this little pathway going out, this line with the enzyme that breaks this down. And so if they really want to be stinky, they squirt this stuff out this little pathway, and it releases benzaldehyde, which in concentration can stink, and HCN, which is not nice. That's what stink bugs do. All right, so the idea was that this benzaldehyde cyanhydrin would be absorbed by tumor cells. The cyanide would poison the tumor cell, and it would die. The problem is that the human gut, the intestine, is a richer source of beta-galactosidase than the typical tumor cell. So, if you go and you eat this stuff, or you take this stuff, or whatever, it's done orally, as soon as it hits your gut, you gas yourself with cyanide, and it can damn near kill you. And almost none of it manages to get its way to the tumor cell. The real thing that Krebs messed up on This is beta-galactosidase, right? There are tumor cells that have higher concentrations of alpha-galactosidase. But the stereochemistry is specific. It only leaves an alpha linkage. This is a beta linkage. And that's what happens in the gut. So this was the wrong isomer. Think back about chapter 6, stereoisomers. This is what's not happening. Any question? Don't eat peach bits. All right. A carbonyl can be so reactive that if you place it in water, it can form what's known as a hydrate. A hydrate is simply water adding to the carbonyl carbon. Initially, we have a Wittig ion intermediate, transfer a proton from here to there, and we wind up with the 1,1 diol. Now, in most cases, this is certainly an equilibrium. Every time you have a carbonyl compound, you will have some hydrate at equilibrium. This is most favorable with aldehydes and teeny tiny bit with ketones. Acetone, 0.1% will be the hydrate. Formaldehyde, 99.9% is the hydrate. Now, actually, formaldehyde hydrate is a very interesting product of commerce. Very highly hydrated. If you take formaldehyde hydrate, you can add another formaldehyde to it. So one of these oxygens to form this guy. Again, we have two more OHs. We can wind up with what's called trioxane. This actually is the formaldehyde that easily, it's a solid, it's easily handled and stuff like that. And again, it's in equilibrium back with formaldehyde itself. Very nice product to work with if you need formaldehyde. This is what trioxane looks like. Kind of a neat little molecule. Instead of reacting with water, we can also do a neat reaction with alcohols. If we take a ketone or aldehyde in the presence of an alcohol, we need an acid catalyst. We can form what's known as a ketal. If it's an aldehyde, it's an acetal. Acetaldehyde gives this acetal. This is a very, very useful molecule. If you want to make it synthetically, this is an equilibrium. And if you, I did put it on here, but if you do the stoichiometry, we're losing 1 mole of water. So if you can do this in such a way that you can remove the water, you can drive the equilibrium this way and make the ketal or acetal. The neat thing about the ketal or acetal is that it's immediately reversible. We take this guy, add acid and water, and boom, we're back to our ketone. Very, very nice reaction. The mechanism here. Now we're going to use the lone pair of electrons on the carbonyl. Step 1, we have to make it more electrophilic. So we're going to protonate the carbonyl. Then our alcohol is going to be invited to attack the carbonyl carbon. and we will form this charged intermediate, which can lose a proton to give the hemiacetal. Hemiacetal or hemiketal means you only have half of it. That's all. Now this can do the same sort of chemistry. Once again, we can protonate this in, which is now water, lose the water, form the oxocarbonium ion like this, add another mole of alcohol, lose our final proton, and we're down to our ketal or acetal. All of this is all at equilibrium. If we want to push it this way, we have to remove water. If we want to push it this way, we simply add acid and water. Very, very useful reaction synthetically. Why is it useful? Because sometimes you will have a ketone that gets in the way that you need to protect. And the way to protect it is to convert it into this 1,1 diether that doesn't react with anything except water. So you can do almost anything with this guy, and then when you're done, you back to where you started. Very nice reaction. Any questions?
Is the stereochemistry from the hemi to the final product always going to be cis to trans or trans to cis?
No, there is no stereochemistry here.
Okay, so it doesn't matter what's
It doesn't matter what it is. No stereochemistry at all. Now we kind of saw this back in chapter 17. Remember I said we would talk about this in a bit? Well, we're talking about it now. Instead of using an alcohol, you can also use a thiol to do this. The classic is to use the dithiol. So this is ethane 1,2-dithiol. And we form this cyclic thioketal. Same chemistry. Okay, same chemistry. But the one unique thing about this is that it ushers in the carbonyl disappearing act. So let's say that we had a carbonyl and you really didn't want it. You just didn't want it there. You could react it, make the thioketal, then simply dump this into rainy nickel, and it totally removes this chunk of the molecule and makes the alkane. Now we'll see that there are several strategies for getting rid of carbonyl. Carbonyls can be very useful synthetically, but sometimes after you use them, you want to get rid of them. This is one of the nice ways. Again, the thioketal, rainy nickel. Rainy nickel is just porous nickel that's been exposed to hydrogen. So it's got it in there already. Just stir it up and poof, you're at the alkane. When we talk about acetals and ketals, I want to stress that this is a very natural sort of process. Think about the structure of a sugar. Okay, when we draw glucose, we draw a 6-membered ring with an oxygen in it, right? That's how we draw it. Well, this is glucose. Here's it. Except this is the aldehyde form. The structure that we draw results from this alcohol attacking the carbonyl, picking up a proton to form a hemiacetal. Now, stereochemically, we can do this two ways. It can attack and form this isomer or this isomer. And these are, this is called the anomeric carbon, and this is beta D-glucose, and this is alpha. It's simply the stereoisomers at the anomeric carbon of the hemiacetal. Isn't that neat? You see, biochemistry really is just organic chemistry on a very nice scale. Any questions? All right, let's do a couple quick problems here. Benzaldehyde, pentanone, this stuff. Go ahead and draw the products. All right, this is standard conditions to form an acetal or a ketal. All in the world you have to remember is that we're going to form a 1,1 diether at the carbonyl carbon. Ether is going to be based on the alcohol that you used. So here, methanol is going to attack, going to lose water, another methanol attacks, and we form the 1,1 diether, the acetal. Just like glucose, except that's a hemiacetal. Everybody's favorite acetal is derived from ethylene glycol. Ethylene glycol is 1,2-ethane diol. And it's an entropy-driven reaction because after you make the first hemiacetal, this guy is sitting 5 centers away, pushes the reaction entropically to form the cyclic diether. Very, very favorable reaction. If you want to protect a ketone, this is the stuff you would use. But actually, it doesn't matter what alcohol you use, even something like cyclopentanol, we're just going to add it twice to our ketone carbonyl here, and we would make something like that. Remember, all of these are easily reversed by just dumping it into water with a little bit of mild HCl. Any questions? All right, so a bit ago, we talked about nucleophiles attacking the carbonyl. Let's do this all the way, and then I'm going to use an amine as my nucleophile here. This is actually a very famous reaction in mechanistic organic chemistry because it led to lots of discoveries in terms of um, catalysis, how these things happen in solution and in enzymes and whatever. Lots of chemistry, biochemistry involves amino groups attacking carbonyls. Well, what's going to happen here is that the nitrogen, the lone pair, is going to attack, and we're going to form this very unstable intermediate. Again, 10 to the minus 8th second lifetime. In order for this thing to survive at all, we have to either remove a proton or add a proton. So here we pull this proton off. This is now much, much more stable. The proton we pull off, we can put up top. Oh, okay, let's do it differently. We can also put the proton here to make this intermediate. And finally, for both of them, we can add a proton, remove a proton, and get to what's called the carbonylamine. The discovery of this was a really important step because carbonylamines, the intermediate for a carbonylamine, leads to what's known as an imine. That's a carbon-nitrogen double bond. The way this happens, we take our carbonylamine. Once again, we're going to protonate. The water is our leaving group. The lone pair will move in. And we wind up with our carbon-nitrogen double bond. This is the ammonium cation. Now, the reason that this is so important is that in amino acid metabolism, you need to get rid of amino groups. You need to convert them into other things. And the way you do this is by making an imine, a carbon-nitrogen double bond. Vitamin B6, I believe, pyridoxal, is the key thing for doing this. You can also do it with pyruvanate, but interesting reaction. There are lots of very simple synthetic compounds that are used to make imines. Let's just run through a list here. Quickly predict the products. Remember, the nitrogen is going to attack, going to lose water, going to lose our proton, and wind up with a neutral compound. Our first compound here is called hydroxylamine. Now today, hydroxylamine is considered a little bit toxic. Oh, back in the old days it wasn't. But this nitrogen is very, very nucleophilic. This is called an alpha effect. Remember, alpha is next to whatever. If we have a nitrogen here, it's next to this oxygen, isn't it? The oxygen has lone pairs, and the alpha effect is basically the effect of these lone pairs on the nucleophilicity of this nitrogen. It makes it very, very nucleophilic. Nitrogen attacks, we're going to lose water, H2O, and we form what's called an oxime. Typically, if you have virtually any carbonyl compound, add hydroxylamine, you can make an oxime very easily in solution. These are beautiful crystalline compounds, very nice to work with. Distinctive melting point, this is how you can identify what a ketone or aldehyde is. This stuff is called semicarbazide. If you ignore the extra nitrogen on the end, this would be urea with a hydrogen here, so this is urea. And we simply have an NH2 on the end. Once again, it's an alpha effect nucleophile, so that nitrogen is very nucleophilic. Semicarbazide will add to form what's called a semicarbazone. And just like this guy, these are beautiful crystalline compounds. Characteristic melting points makes it very easy to identify what ketone or aldehyde you have. Our last one here, this is called 2,4-dinitrophenylhydrazine. So it's kind of similar to this. Again, it's an alpha effect nucleophile. This is the basis of a qualitative test. Let's say I gave you something, and I just asked you, is this a ketone or an aldehyde? I don't know. Well, the way you would know, the way you could test for it, is you would use what's called 2,4-DMP reagent, which is just this stuff in acid. You dump it in. If it is a ketone or aldehyde, they react. They form the phenylhydrazone, this guy, which is a brilliant yellow precipitate, always insoluble in water, falls out directly. Beautiful, again, beautiful crystals. This is the heart. These guys are really the heart of qualitative organic chemistry. Back in the old days, for lab, we used to do things like give an unknown, add 2,4-DMP reagent, and identify the compound. I think that's still kind of neat. Now you can use any amine for this. Go ahead and quickly draw the amines that we get from these guys. All we're going to do here is take the nitrogen, we're going to add it. We're going to lose the elements of water, make a carbon-nitrogen double bond. This is the ethylamine imine of acetone. If we use aniline, the chemistry is exactly the same. We lose water. That's H2O. Nitrogen bonds to the carbonyl carbon, and we form this guy. Now you'll note that both of these I've drawn as neutral species, right? Because it's all equilibrium. If they were an acid, they'd be protonated, but basically you would isolate them as neutral species. Here we have a secondary amine. Now with a secondary amine, you can't make a neutral species, can you? So this guy is going to add to make the ammonium cation. Now this is a neat thing because later in this course, chapter 2021, we're going to use this imine as a nucleophile. Basically, here's what's going to happen. If we take a ketone or aldehyde, react it with a secondary amine, we make an ammonium, IMM, cation. Now this is unstable, isn't it? Sort of, because it's charged, doesn't want to be charged. But it can become neutral by losing an alpha hydrogen. Base pulls this off, and we get this guy. And we will call this an enamine. Alkene amine. Now the reason that this is so neat is that this process is at equilibrium. And we can take these electrons, move them back, and put a carbanion on this carbon. So here's our enamine. We're going to move these electrons down, move these guys out, and we have a carbanion. Later on in the course, we will use this carbanion as a nucleophile. The enamine carbanion we can add to other carbonyl carbons and to a whole bunch of other stuff. Very, very powerful nucleophile. Nice way to convert a carbonyl into an alpha carbanion. Now we talked about hydroxylamine, we talked about semicarbazide, 2,4-DP. This is hydrazine. Hydrazine is a rocket fuel. Anytime you have two nitrogens that are too close to each other, they really want to be nitrogen gas. Okay, so it's a fairly unstable compound. But hydrazine, just like any other alpha effect nucleophile, can attack the carbonyl to form a hydrazone. Now, what makes this especially interesting is that the hydrazone, once again, the nitrogen wants to be nitrogen gas, can undergo an elimination reaction. The elimination is something like this. If we take strong base, we can do what's known as a reductive elimination to get nitrogen gas and the hydrocarbon. All right, what are we talking about? Our base pulls off the proton, wind up with this thing, we put one proton on, gonna pull this proton off. Here's our nitrogen gas. By George, we just made a carbanion, but we're in the middle of an aqueous sort of solution, so this will instantly pick up a proton. And by gosh, our carbonyl disappeared again, and we're back to a hydrocarbon. This is the Wolff-Kishner reduction. Wolff-Kishner reduction. Let's go back so I can show that. Wolff-Kishner basically takes a carbonyl hydrazine and makes a hydrocarbon. The great carbonyl disappearing act once again. Turns out that there's another way we can do this as well. This is called the Clemmensen reduction. Clemmensen reduction. It's a dissolving metal reduction, okay? Dissolving metal. If you want to do a dissolving metal reduction with zinc, you would put zinc in there with acid. As in physics, it takes hydrogen radicals. Okay, that's what the fizzing is, hydrogen radicals. And you can use this for various things. The Clemmensen reduction, originally, Clemmensen didn't do this. Some lowly person that he paid to sit there in the lab did it. Was trying to do a dissolving metal reduction on a carbonyl. Wasn't working. Nothing was happening. He had a thermometer in there. You could tell nothing was happening. No heat. And he was stirring it vigorously. Well, the thermometer broke. Mercury went in, formed a zinc-mercury amalgam, which is the magic component, and suddenly the reaction went. So Clemmensen got his name on it. Clemmensen reduction, carbonyl zinc-mercury amalgam in acid. Again, the carbonyl disappears. This works very nicely, actually. Here's an aldehyde, again, straight to the hydrocarbon. All right, let's just do a couple. These are examples of a Wolff-Kishner. Go ahead and draw the hydrocarbon products following the Wolff-Kishner reduction. Very simple reaction mechanically. All you have to do is look at your carbonyl and remember that that is going to be a CH2. Carbonyl becomes a CH2. Here we have ethylbenzene, and down here we would have methyl cyclopropane. Yeah.
Is it always in KOH?
Yep, KOH, good strong base. So in terms of our great carbonyl disappearing act, there are 4 ways that we know to do this. Back in 234, you learned that you could take a carbonyl in the presence of hydrogen, platinum, or palladium on charcoal. You could reduce the carbonyl to a CH2. This is our Wolff-Kishner, hydrazine and KOH. Again, carbonyl to CH2. Clemmensen reduction, carbonyl to CH2. And finally, don't forget our smelly friend, butane thiol. Here we have our 1,2-butane, or ethane thiol, 1,2-ethane thiol. Going to make our cyclic thioketol, radionickel, and again, carbonyl to CH2. Any questions? All right, let's review quickly what we said about carbonyl compounds in chapter 17. Recall that carbonyl compounds react with lithium aluminum hydride. Lithium aluminum hydride donates an H minus. It goes to the carbonyl carbon. We pick up a proton, and we simply make the alcohol. Lithium aluminum hydride is a wonderful reagent. It is, however, somewhat dangerous to use. It's flammable in air. You have to do the reaction in ether. Ether itself is explosive, and so you have to be really careful with it. Much simpler and better way is to use borohydride. Borohydride works very nicely. The selectivity, however, is not nearly as good as lithal. For this, where we have multiple functionalities, a ketone and a double bond, we get 94% of the desired stuff. With borohydride, we get about a 50-50 mix. So lithal is better. Borohydride is much safer, much easier to use. Let's review some of these. Quickly jot down the reduction products for the borohydride reduction of these carbonyl compounds. All we have to remember here when we're doing reductions, if we're going to add H- to the carbonyl carbon and make it an alcohol. That means that cyclohexanone, going to add H- right here and simply make cyclohexanol. Benzaldehyde with borohydride, going to add H- to the benzyl carbon, and we will make benzyl alcohol. This is acetophenone. Add H- to this carbon, and we will make alpha methyl benzyl alcohol. Chapter 17 stuff, any questions? Continuing with chapter 17, let's just review what we said about Grignards. Same sort of chemistry. Instead of H-, we're going to add an R-. That is a carbanion. Same sort of chemistry. This is a positive center. We simply add, we form this intermediate. Going to protonate this, and we're going to make an alcohol. We've done these, very quickly run through them, and draw the products for these Grignard additions. Remember, you simply identify the carbanion. It's the thing that was attached to the alkyl halide, to the halogen. So in this case, it's simply a methyl group. It's going to add to the carbonyl, and we will form 2-propanol. Grignards work nicely with aromatics. Here we will form phenyl magnesium bromide. It will add to this carbon, and we will form alpha methyl benzyl alcohol. Bromocyclohexane. Take the Grignard, that's a carbanion. At that point, it will simply add to the carbonyl carbon, and we will form our tertiary alcohol. Any questions? Now, I was very upfront with you. We had this quiz, and I told you that you will get Grignard questions on this exam. And here's an example again of what you might get. I want you to make this secondary alcohol two ways. So very quickly come up with the two parallel pathways we could use to make this alcohol using a Grignard synthesis. Remember, what we do is we look and we say, okay, this OH group used to be a carbonyl. It's a secondary alcohol, so it used to be an aldehyde. And we want to split it on both sides to get the two potential pathways. So we're going to take and we're going to split on this side or this side, identify the carbonyl, and identify the Grignard reagent. If we split here, then our carbonyl was on this side. This used to be a carbonyl carbon with 1, 2, 3, 4, so it's a butanal. And our Grignard had 1, 2 carbons. So butanal and something like bromoethane should work. Now if we split on the other side, now we have 1, 2, 3 carbons, so it's a propanal. And our Grignard had 1, 2, 3 carbons, so it's a propane. So it's a bromopropane would work nicely. Something like this should work. Make sure you master this skill. We'll actually see it again in just a couple minutes. But make sure you understand the symmetry for simple Grignard reactions. Almost all of them you can do two ways. If you're using formaldehyde, you can't. But almost all of them you can do two ways. And it's a very nice synthesis. There are problems with Grignards, however. Remember those. Anything with an acidic hydrogen is going to break down the Grignard reagent just to an alkane. And if you have any other reactive groups, it's probably not going to work. Any questions? Well, in chapter 17, we also introduced alkyl lithiums. Now, we're going to use alkyl lithiums a couple ways here in this chapter. But let's just review what they are. If you take an alkyl halide and lithium metal and ether, you can make an alkyl lithium compound with a very, very polar covalent bond. This is very cationic, and this is essentially stabilized anion. Now with carbonyls, what we do is simply take the anion portion, just like a Grignard, we add it, and we form our intermediate, which we're going to protonate, to give our alcohol. Very simple anion addition alcohol. The neat thing about an alkyl lithium is you can use primary, secondary, tertiary, alkyl, aryl, or vinyl. and they're all very good nucleophiles. So let's look at an example. Here we have a vinyl lithium compound and benzaldehyde. Just quickly jot down the structure of our atoms. I like this one because it's difficult to conceive unless you kind of understand what's happening. In this case, what you want to simply remember is that this carbon right here, the vinyl carbon, is the carbanion. So we're going to form a bond from it to this guy. The bond's going to go from here to here. That's our carbanion. And our attack looks like that. So we're going to have a bond now from the carbonyl carbon to this vinyl carbon. And this is the alcohol we wind up with. This is the bond we just made. And this used to be a carbonyl carbon. Simply think of it as a C minus. All right, enough of chapter 17. Let's move onward to an absolutely magic reaction. Absolutely magic. It's called the Wittig reaction. Wittig with a W. He was German. This involves what's known as a phosphorus ylide. Phosphorus ylide is made from a triphenylphosphine, so 3 phenyl groups here, an alkyl halide, and again, this is a carbanion. The phosphorus is positive. When you have a plus and negative next to each other, it's called an ylide. If you want to make monodi and tri-substituted alkenes, this is amazing. Can't do it with tetrasubstituted because it's too crowded. But basically what you do, you look at your carbonyl, right? Here we have R2C. We're going to rip the carbonyl oxygen off and put this on. It's just magic. You dump the oxygen and you put this on as an alkene. Same double bond. It's just suddenly you have this stuff instead of your oxygen. An amazing reaction. You make this ylide, again, from triphenylphosphine and some alkyl halide. Phosphorus attacks, the bromine leaves, and you get this stuff. This is a phosphonium salt. Not an ylide yet, it's a phosphonium salt. In order to make the ylide, we have to pull this hydrogen off. But because it's next to the positive phosphorus, it's fairly acidic. Typically, this is done using what's known as N-butyl lithium. Again, this is an alkyl lithium. It behaves like a carbanion, so it's really, really basic. And it'll just rip this hydrogen off, and when it does, you make your ylide. Very, very nice, sweet reaction. Again, alkyl halide. to our aldehyde. Now, how does this magic work? Well, quite obviously, the first step is going to be the carbanion attacking the carbonyl. We've all figured that one out. We get this intermediate. Now here, unlike, say, the Grignard reaction or the alkyl lithium, we wind up with an oxygen next to a positive phosphorus. Well, this is O minus P plus. This is going to cyclize to form this four-membered ring. Plus and minus, they can hardly avoid each other, right? Once you make this four-membered ring is going to break down. Oxygen is going to go with the phosphorus. This half is now your alkene. So you form this four-membered ring intermediate, break it down this way, oxygen goes with the phosphorus, and here we have our double bond formed. Beautiful example of chemistry. Let's see how we might use this in a synthesis. Let's pretend we were given cyclohexene and we wanted to make this stuff, methylene cyclohexane. Well, we're obviously having to add a carbon, aren't we? Not a trivial thing. But, considering we just did the Wittig reaction, we know that if this had been a carbonyl, that we could stick a CH2 there using a Wittig reagent. So in our head we're saying, I can make this alkene using a Wittig reaction if I had the corresponding carbonyl. So what's the corresponding carbonyl? Well, this used to be an oxygen, right? And what's our Wittig reagent? It's this stuff, CH2 triphenylphosphine dilute. There we go. Now we've added the extra carbon. So our new synthetic problem is, how do we go from cyclohexene to cyclohexanone? Well, we say to ourselves, we could make cyclohexanone if we had an alcohol, right? We could do that. If this was an OH, we could oxidize it to the ketone. So we could do that quite simply if this was an OH using, lots of different oxidants. Let's just use PCC because we can. Now our synthetic problem is really 234-ish. We're starting with cyclohexene. We want to make cyclohexanol. We know 3 ways to introduce the OH group. One is brutal, acid and water. Don't ever use that, that's ugly. Get tar. Second way, we could use borohydride. BH3, followed by oxidative workup. Since it's symmetrical, it doesn't matter if it's Markovnikov or not. Or we could do a more civilized Markovnikov addition using mercury 2 acetate. That's generally my choice. Mercury 2 acetate, followed by borohydride reduction to give us the alcohol. questions? This is 235. Now remember how we talked about how neat Grignards were because there was a symmetry to the reaction? Well, guess what? Wittig reactions have a symmetry of their own. Give me two ways to make this molecule using a Wittig reaction. What you have to remember is that you look at your pair of sp squared carbons, okay? In one reaction, this guy was a carbonyl. In the other one, this one was a carbonyl. That's all you have to think about. If this guy was the carbonyl, what would it be? Acetaldehyde. CH3, carbonyl, hydrogen. What was the Wittig? This stuff, as the triphenylphosphine ylide. Oops. Acetaldehyde is this stuff, as the ylide, lose our oxygen, and make our double bond. The other way to do it, this guy used to be the carbonyl. That means that this was the ylide. So this is going to be cyclohexanone, and this is going to be methyl CH hydrogen as the phosphonium ylide. Just like a Grignard, nice symmetry. Any questions? All right, now I'm going to take you back to the very early days of 235. When we talked about additions of something like HBr to a diene, we said we could get 1,2 and 1,4 addition. That's because the carbocation was resonance stabilized, and we had positive character on carbon 2 and on carbon 4. For the 1,4 addition, we simply added here. Everyone remembers that, right? Well, let's take that concept, again, adding here, 1,4 addition. Let's take this same concept and apply it to an alpha-beta unsaturated carbonyl. Alpha-beta unsaturated carbonyl looks a whole lot like a diene, doesn't it? It does. And we've done additions to the carbonyl. That would be the equivalent of 1,2. Well, by George, you can do 1,4 addition as well. Because this guy exists as these two resonance forms. This is our standard carbonyl addition, 1,2 if you will. And this would be 1,4. So if you have an alpha-beta unsaturated carbonyl, you can do 1, 2, or 1, 4 additions. Yeah.
Just to review, the alpha is the double bond furthest from the oxygen?
Alpha is right next to the carbonyl, and beta is the one next. Later on, we're going to do gamma too. That's the one out here. So if I take a nucleophile and an alpha-beta unsaturated carbonyl, I can add. Then when I pick up my proton on the O-, I have still a carbonyl, but now I have a nucleophile tacked on here to the beta position. Now think about how powerful this is. We know lots of nucleophiles, don't we? We can extend this chain lots of different ways, make lots of different functional groups. Very powerful reaction. Let's look at some examples. Amines are very good at doing additions to an alpha-beta unsaturated carbonyl. Here, the nitrogen is simply going to attack the beta carbon. When it does, electrons will flow, make the oxyanion. Here we have our oxyanion there. Our final product, after we pick up a proton, we have the amine bonded to our beta carbon. So step one, we attack. Our double bond is initially here. That's an O-. Pick up the proton here. We're back to our carbonyl, except we've added our functional group. Go ahead and draw this product. Again, the nitrogen is the nucleophile. We're still going to wind up with a carbonyl. It's just we've added our nucleophile to the beta position. Electrons move up, get the oxyanion, pick up a proton on this, and we made this addition product. Now, after our discussion of Lantril and cyanide and stuff like that, cyanide might not be your favorite compound, but cyanide is a very good nucleophile also. And we'll see in chapter 20, which is coming up someday, that cyanide can be converted to acyl derivatives fairly easily. So it's a nice, simple nucleophile. The cyanide that we tend to use is diethyl aluminum nitrile. Diethyl aluminum nitrile is a nice, convenient, soluble cyanide compound. Once again, the Cn- is our nucleophile, and it will simply add to our beta position. For our first compound, this is going to add to there. Once again, we get an intermediate with an oxyanion, pick up a proton here, and that's our product. We do this with cyclohexenone. Same sort of thing. Going to add the carbon to this point, oxyanion, pick up a proton here, and we get this ditrile. If you think about it synthetically, we've added a carbon atom here. And again, when you're doing synthesis, you want to build a chain. So this is a nice way to introduce a single carbon atom. Now there's another very good nucleophile that's related to our alkyl lithiums. And these are the dialkyl copper lithium complexes. Dialkyl copper lithium you make from an alkyl lithium in the presence of copper, kind of a big messy black gunk, to be honest. But this stuff at some stoichiometry exists in there. And the carbon is once again a carbanion. Dialkyl copper lithium, they can donate this carbanion to our beta position. Now we've simply added a methyl group out here, and we've extended our chain. Just like a simple alkyl lithium, you can make a dialkyl copper lithium from darn near anything, darn near any alkyl halide. Here we're going to add our vinyl carbon, so this CH is our nucleophile. Here's the thing we added. Our CH is our nucleophile. Simply adds to the beta position. And by George, look what we've made. Again, the magic just goes on and on and on. Any questions? Let's just look at a few. What I'd like you to do here is to look at cyclohexanone and give me an idea of what reagents you might use to make these compounds. So this is kind of like a simplified synthesis. You're starting here, you're going here. What reagent would you use? Now for a first one, you want to sit there and say to yourself, what have I done? Well, I've added a methyl group to a beta position of an alpha beta unsaturated ketone. I've added a methyl group. And we have picked up a proton here, and we still have our ketone. So this is a classic example of the adding a methyl group reaction, right? Which we just talked about, the dialkyl copper lithium, right? So we want dialkyl copper lithium, and the alkyl group we want is simply a methyl. Our next reaction, we're making a doubly bonded nitrogen with an OH. Remember what these were called? These are called oxenes, aren't they? And they're from hydroxylamine, NH2OH. Nice specific reaction at the carbonyl carbon, doesn't bother the double bond. Hydroxylamine looks like this. In our next one, we're doing the magic disappearing oxygen act. Now we know 4 ways to do that, don't we? We can do the thioketone. We can do Wolff-Kishner reduction. We can do Clemmensen reduction. We can go back to 234 and do hydrogen and platinum, palladium, whatever. Any one you wanted to choose would work. Wolff-Kishner, Clemmensen, thioketone. Let's just do Wolff-Kishner because we can. All right, same story here. What have we done? We've added a phenyl group to our beta carbon. Now, this is the beta carbon down here, but I flipped it around so it fit better. But it's still a beta carbon, isn't it? How do we add an alkyl, aryl, or vinyl group? Dialkyl copper lithium. What do we want here is a diaryl copper lithium, simply with benzene as our nucleophile. So we want 2 phenyls and copper lithium. What's this strange thing that looks a little bit like a spider, except it's busy a set of legs? But what is it? It's an enamine, isn't it? Alkene and amine. Enamine. How do we make enamines? Take a carbonyl compound. We're going to add a secondary amine. We're going to lose a proton, and it's going to form a neutral enamine like this. Secondary amine we need here is simply diethylamine. Again, we attack the carbonyl, we lose water, lose a proton, and we're here. Our next one is a 1,1-diether. That's called a ketal, isn't it? We simply make ketals by taking the carbonyl in the presence of alcohol and acid. To drive it to completion, we have to remove the water. We can do that. All we need here is methanol in the presence of acid. Starting with benzaldehyde now, just to mix it up a little bit. What have we made? We have made a secondary alcohol. Oh, that's simple. We know lots of ways to do that. All we have to do is reduce the carbonyl to an alcohol. 2 ways. The fun way is to use lithal, or the safe way to use more hydride. Oh, wait a minute, I'm sorry. Let's start over again. We have a methyl group here now, don't we? So this is a Grignard addition. I'm sorry. I missed it. But So we're going to add a methyl Grignard to benzaldehyde to make our secondary alcohol. Our Grignard is simply methyl magnesium bromide, followed by workup with dilute acid. Our next one, once again, the amazing disappearing carbonyl. We know 4 ways to do this, don't we? Thioketal, Wolff-Kishner, Clemenson, or platinum palladium. Platinum palladium, or hydrogen platinum palladium on charcoal, works fine, especially for a benzoic center. We'll use that. Nice and simple. Our last compound here, this is an imine, isn't it? Carbon-nitrogen double bond. How do we make that from a carbonyl? Simply by adding the amine and dehydrating. The amine we need would be this half, whole top half. So this is going to be benzene ring with NH2, that's aniline. It's an imine, going to use this as our amine, and that's all we need. Last one here. Again, benzaldehyde to benzoic acid. If you have a real bottle of benzaldehyde sitting around the lab, it's always crusted with this white flaky stuff. That's benzoic acid. That's because aldehydes oxidize so easily. So all we have to do here is oxidize this to this. Because we're oxidizing, we could use almost anything. Chromate works nicely, cleaning solution. So chromate and sulfuric acid. And we're there. Once again, a 1,1-diether. The alcohol here is going to be this half. That's ethene with 2 hydroxyl groups. So 1,2-dihydroxyethane. Ethylene glycol. And we simply need an acid catalyst. Got a 1,2-diol, and that should work. And finally, now we're taking benzaldehyde to benzyl alcohol. This is the reduction reaction I wanted to do initially. Again, we can do it the fun way with lithiol, dangerous but fun. Or we could do borohydride, much more conservative. All we have to do is reduce. Borohydride does it fine. Let's turn this around. On the exam, you will have reactions like these, syntheses like these. You'll also have simple reactions. Let's just practice some simple reactions. It's a 1,2-diol in the presence of acid. What are we making? We're making a ketal. That's a 1,1-diether. It's a 1,2-diol, so it will be cyclic. And it will look like this. Our next one, we're simply adding a Grignard reagent. So we look at this carbon, that's our nucleophile. It's going to add to the carbonyl carbon. We have an aldehyde, so it's a secondary alcohol. All we have to do is draw a bond from this carbon to the carbonyl, make this an OH, and it should look like that. Here's the bond that we just made. This guy, we have hydroxylamine, and we have a ketone. We're simply going to add the nitrogen here, make a carbon-nitrogen double bond, and make the corresponding oxime. Let's do one more in this set. Pyridinium chlorochromate, mild oxidizing agent. It will not oxidize an aldehyde. This is a secondary alcohol, so we're just going to make a ketone anyway. Doesn't matter. Still works. Going to convert the OH into a carbonyl. Or a hydride, simple reducing agent. Add hydride to the carbonyl carbon, make an alcohol, and we have 2-propanol. Finally, if we have our cyclic ketal and we dump it back into aqueous acid, what happens? We're going to make our ketone again. So this carbon is now going to be a carbonyl, and this is going to be a 1,2-diol. Any questions? I think on the handout there are a couple more pages of reactions. You can do those if you have a question. Ask me about it next week. Let's just go ahead and skip on to a Wittig problem. Again, classic exam question. Make this alkene using a Wittig reaction 2 ways. All you have to remember, these are your sp² carbons, right? In one method, this was a carbonyl. In the other one, this was the carbonyl. That's all you have to remember. Let's split it. This half, if this was our carbonyl carbon, we would have a 2-carbon aldehyde, and that would be acetaldehyde. This half, all of this, would be our Wittig reagent. Remember, our Wittig reagent is simply this attached to a triphenyl phosphonium salt. Here's this part. That's the anion, triphenyl phosphonium, and this is our aldehyde. If we do it the other way, if this was our carbonyl, then this came in as our Wittig reagent. So this was an aldehyde, and this is a 2-carbon chunk. So we have 2 carbons, instead of all of this, as an anion bonded to triphenyl phosphate. And the pair just looks like this. Any questions? So let's finish this up with our favorite symmetry reaction, our Grignard, again to show you just how nice symmetry is in organic. Make this guy 2 different Grignard syntheses. Remember, the OH was a carbonyl at one time. So we either added this chunk or we added this chunk. That's all you have to remember. It was a carbonyl, so we added this or we added this. Let's cleave on this side. So our carbonyl had the carbonyl carbon, 1, 2, 3 additional carbons. So it's propanal, 3 carbons. This side, our Grignard, this is an isopropyl group, isn't it? So this is simply isopropyl Grignard. Isopropyl magnesium bromide. 4 carbons, I guess. I said pro. This is butanal. That's close. And they would look like that. Now, if we cleave on the other side, then our carbonyl compound has 1, 2, 3 parent chain. So that's a prop. It's a 2-methyl propanal. That's part of that. And we've simply added a 1, 2, 3 carbon chunk. So that's a propyl magnesium bromide. Two-methyl propanal, propyl magnesium bromide, and they should look like that. And I don't know about you, but I'm tired. There's a lot in this chapter, but it gets worse. The chapters that are coming, we're going to do even more, especially when we do condensations and cross-condensations. It's going to get a little more complicated and stuff. But this is your basic background for carbonyl chemistry. Again, we're going to be doing this all the way through chapter 22. Any questions? The